welcome to Wednesday's edition of Cracking the Cryptic, and a debut on the channel today for Emmett Nelson. Some of you may know Emmett better as Emmett Saito, which is his handle on Discord, and this puzzle is called Heterochromia, which I think means different colours, which sounds right up my street. This puzzle has been recommended to us, well, a lot of times in the last few days, and that is because of an astonishing collection of comments I think it's been garnering on Logic Masters Germany. So I'll try and put some of them on the screen there now, but you can see people like Sudoku Explorer saying that this is one of the best puzzles they have ever seen. So this ought to be absolutely incredible, and to be honest, I'm slightly surprised as I stare at it now that it has a solution, because there don't seem to be very many. In fact, there's only 10 cages. 10 cages in the grid, none of which are greater than 4 cells large. That's astonishing. That is astonishing. A knowledge bomb from Cracking the Cryptic, a 9x9 Sudoku grid, has 81 cells. Well, in this puzzle, less than 40 of those cells are filled. And apparently the rest of them can be filled just using the logic that these cages provide. So quite amazing. And yeah, we'll have a look at the rules in a moment, but it's normal killer Sudoku, so nothing complicated. Other news, just a huge thank you to those of you who support the channel over on Patreon. You keep us going, and we do try and make it well, more than worthwhile with all the extra content we put over there. And today we've just posted Mark's battle with the vicious cryptic crossword, the Times Monthly special. That video is over an hour long, which gives you an idea of just how hard that puzzle is this month. So do have a look at that if you like the crossword content. And of course there's April's reward puzzle as well. Everything Is Wrogn is on fire by DiMono. That is an awesome puzzle, so yeah, check it out. Right, and with that, what are the rules of Emmett's puzzle? We have got normal Sudoku rules apply. In cages, digits must sum to the small clue in the top left corner of the cage. Digits cannot repeat within a cage, and that is it. And as ever on Cracking the Cryptic, if you'd like to have a go at the puzzle, and we certainly recommend it, the way to do that is to click the link under this video and you'll come to a page that looks identical to this one, where you can play the puzzle on whichever device takes your fancy. Now I get to play Let's Get Cracking. Let's Get Cracking. I mean, I'm no longer surprised by this at all, but you can see if we look at all these cages here, none of them really rings a bell with me. I mean, I know a 14 cage in 4 cells can be missing a 1, because 2 plus 3 plus 4 plus 5 adds to 14. But that's sort of negative information that's not maybe the most helpful. Yeah, I mean, this is immediately looking very tricky. It looks like there might be something going on between column 5 and row 5. Simply looking at the sizes of the cages, I mean, a 27 cage and a 26 cage, they're reasonably large numbers. A 14 cage and a 14 cage are reasonably low numbers, which implies this cell is under tension. So what we should probably do is write 5 in there and go on, but that's a bit of a guess. Okay. Wow. Wow, wow, wow. How do we get started here? I guess we have to think about, well, I'm not sure. Let's think about what's the minimum we could make these cells in column 5. So if I was to put a 9 here and a 9 here, that's 18. We know these cages sum up to 53. Oh, that is it. That's okay. Well, that's immediately a little bit interesting. That means actually I can't put 2 9s here and here, Because if I do, I can no longer put a 9 in the column because of the secret. The secret, of course, is something we only tell our favourite people. But I've decided that you're amongst them. So what does this column of the Sudoku sum to? Well, the way to work that out is to realise that any complete column of a Sudoku will contain all of the digits from 1 to 9. If you add up those digits, you get 45. So these yellow cells here sum to 45. Well, if I put 9s into those two squares, these 6 squares sum to 35, and therefore those squares in the gaps have to sum up to 10. Now, can any of these cells then be a 9? No, because if I put a 9 here, that would imply those two squares had to add up to 1, which is impossible. So you could no longer put a 9 in this column. So at least one of these squares is not equal to 9, which means that the maximum value of these squares, let's just check this again. So we've now got 17 here, which means we've got 36 as an absolute minimum in the yellow squares, which means that these squares have to sum up to a maximum of 9. But we don't know what those squares are. We just know these squares do have a relatively small total. And we'll start the colouring on that basis. So, what does that mean? So it means there's no 9s, 8s or 7s in the purples, because we know these three squares sum to 9, and you can never use 7, 8 or 9 in a 3-cell sum that adds to 9 without repeating a digit. So is this the break-in then? Am I meant to be thinking about... I'm meant to be thinking somehow about what can go into those squares then. Not sure. I can't really see much else to do. So, I mean, I guess what we have to think about is how high we can make these squares. So, if we make these really low... Oh, that's interesting. I was going to say if I make those really low and I was going to put 1s into both of them, which I can do by the power of Sudoku, look, that's not going to clash with anything. But, if... Oh no, I could put 1... Oh no, I can't put 1 there. No, I don't think I can do this. Because if I do this, I can't put 1 in any of those cells. So surely, in order to minimise the value of these squares, it's going to be sensible for one of them to be a 1. So let's do that instead. So now we've got 3 in those squares, which means these squares have a minimum value. Sorry, a maximum value. What am I talking about? Of 25. 25. Yeah, I mean, these are 25 or lower, aren't they? As I increase this, I'm going to reduce this. So the maximum value of the squares in yellow is 25. The maximum value I could put in here is 6 in order to make sure that these purples stay adding up to 9. So the absolute maximum that these 7 squares can add up to is 31. So the absolute minimum of those squares on the edge is 14. So we know therefore that they have to be no lower than 5. And is the same thing is presumably true in this row as well. Yes, it's exactly the same logic. Right, okay. That's fine. We've got some relatively high totals. Each of these sort of extraneous regions, or these two squares, have to add up to at least 14. Those two squares have to add up to at least 14. Let's get rid of the 1 and the 2 because we don't know if they're correct. No. Sorry. I could have... No. This is a much better question. Where does 9 go in row 1 of the grid? You can never put a 9 in a 14 cage, ever. We've worked out the purple can't be 9, so those squares can't be 9. There's a 9 in one of those two squares, and the same thing is true in row 5. So there is now an X-wing on 9s in columns 1 and 9. What do I mean by an X-wing? Well, if we think about the logic, if we know one of those two squares is a 9, and we do, and we know one of those two squares is a 9, and we do, then in the finished solution there'll either be a 9 here and here, or there'll be a 9 here and a 9 here. Either way, we can't add more 9s to these columns, so none of those squares can be a 9. And that, does that matter for the 23 and the 22? I'm not sure, actually. Oh, there's a small point I can see around the 23 and the 22. 23 and 22, here's a knowledge bomb, add to 45. Now look, the whole column adds to 45. So in fact, you know that those two squares must add to exactly the same as those 3 squares there, which is a little bit interesting. I don't really know what to do with that. I guess if these two, therefore, if that was 9 and that was its minimum, which would be 5, that's 14, 15. So these, so those squares have to add up to at least 15. Okay, that's good. We'll put that in. 6, 7s, 8s, and 9s into those squares. Right. So actually that X-wing doesn't seem to do that much. Right. Okay. So now I'm stuck. What on earth am I meant to do now? These 14s, they must... These can be 1 and 2. Sorry, I'm not exactly seeing, as you could see, I'm not exactly seeing what I have to do here. I might be able to limit those two squares, actually, thinking about it. Because there must be a 1 in those squares, isn't there? Maybe that's what I'll do. Right, let's work that out. If this is 2, 3, 4, 5, 6, 7, so if we try and not put a 1 in the 14 cages in row 1, 2, 3, 4, 5, 6, 7 is 27. Ah, that's good. Okay, so it's just good enough. If those squares add up to, had no 1 in them, that would give us 27 in these 6 cells. But we know that the 2 cages together add up to 28, so these 2 squares would have to add up to 1. So actually 2 is going to be the same, I think. Let me just check that. So now let's try it differently. Let's try it with 1, 3, 4, 5, 6, 7. So that should add up to 26, and does. yeah, and that breaks as well. Because now those two squares have to add up to 2, and you can't do that. Because that would cause double 1 into those positions. So actually, we can rule 1 and 2 out of that purple square, which is nice. Because we know, and this pencil marking is not going to be terribly good, I'm afraid, but I know there's a 1 and a 2 somewhere in those 6 cells, so I am misusing my own pencil marks hugely there. So this square has to be a 3, 4, 5 or 6, because we know these 3 have a maximum value of 9. Now, can I do the same thing here then? I can definitely get rid of 1. I'm not sure about 2 because these 2 are not in the same row. Oh no, I can. Right, it's the same logic. Look, if this is, let's look at it with 1 first. Let's try and miss the 1 out. This is the easy way of doing it. This is exactly the same logic as this. So now those squares are adding up to 27, which means those two squares have to add up to 1, which is impossible. We can't use 1 and 0. But in actual fact, if we were to do this instead, 1, 3, 4, 5, 6, 7, now these add up to 26, and at first blush we might think we can go double 1 here. Well, we can't, because double 1 here removes the possibility of this square being a 1. So our whole premise for thinking 1, 3, 4, 5, 6, 7 was possible is broken. So you can't do this, so it's also fair to say that these squares here also need a 1 and a 2, and that means this square also is 3, 4, 5 or 6. Now these two now have a minimum value of 7, so this square is either a 1 or a 2. And we can get rid of 6, because you can't now use 6, 1, 2 as an option for this column. That's lovely. No. Got more. And, yes, and where does 1 go in column 5? The answer is there. It can't go. You can't put a 1 in a 4-cell 26 cage. The other 3 cells would have to add to 25. 7, 8 and 9 add to 24. And it's even worse in a 27 cage. We have a digit. It's taken a long time, but we have one. We have a 1 here. Yes, and we have a 2 in there. Because 2 can't ever go in a 27 cage. You'd have the 3 cells adding to 25 problem. So there's a 2 in one of those. And look, that means the other cells in this cage add up to 24. They are 7, 8, and 9. Ooh. Now, let's see what we can get from this. We can... Oh, come on. I don't know. Can we get anything from it? Something. These two squares now can't be a 4-5 pair because 4 plus 5 plus 1 is 10, and we know the maximum value for the purples is 9. So there's a 3 in one of those. I'll adulterate my pencil marks again. So if there's a 3, surely that's going to put incredible pressure on the 14. Let's just look at that. Sorry. If there's a 3 here, I'm thinking now the minimum value of these 6 squares would be 1, 2, 4. 25 would be the minimum. Yes, and we know we can't use double 1 ever in the wings of these 14 cages, because then we can't put a 1 in the 14 cages in the right rows. So wherever the 3 goes, and we don't know where it goes, but wherever the 3 goes, it has a 1 and a 2 in these positions in order to make the 14 cages possible. So 3, wherever it lives, accompanies a 1-2 pair in these wings. Yeah, okay, but we can go further than that, because 3, 1, 2, 4, 5, 6, 7. Yes, 3 also, in order to make the 14 cages possible, you've got to keep 8 and a 9 out of them in a row where 3 is here. So there would have to be the 8 and the 9 in the wings of that row. So whichever one of these rows has a 3 in it also has an 8 and a 9 in it. In sort of column 1, column 9 positions. But the problem is we don't know what the other digit is. It could be 4, it could be 5. Sorry about this. I'm now stuck. Maybe I think about 5. If it was 5, you'd have 1, 2, 3, 4, 6, 7 as the minimum in those squares, which is 17, 23, is it? 1, 2, 3, 4, 6, 7. 17 and 6 is 23. Plus the 5 in the middle is 28. So you'd have to put 8 and 9 in here again. But if you did that, you'd have degrees of freedom. That's the point, isn't it? Yeah, okay, I see. If you do that and you put 1, 2, 3, 4, 5, 7 there, of course you have to put 8 and 9 in the wings, but the point is that you've only reached 23 as a total for the yellow squares in the 14. So there are lots of degrees of freedom for these squares. These squares have to add up to 5, and we can increase these. And if we do increase these from a 1-2 pair, we'll reduce those two squares. Ah, okay, bobbins. Right. So what does that mean? I don't know. Right, no, hang on. Let's approach this more simplistically, I think. Just look at this row, this top row. How many big digits can you ever put in the 14 cage in row 1? You can only put one big digit in any 14 cage. You can't put a 6 and a 7 in there, for example. That's going to break. So each of these two sort of 3-cell strings can have exactly one of the digits 6, 7, 8 and 9 in it. Now there are 4 such digits in the whole row because 6, 7, 8 and 9 is 4 different digits. If you can only put one of them in each of those strings and you can't put one in the middle, one of them must go in the edges. So you can get rid of 5 from those squares and you can get rid of 5 from those squares. And we will be grateful for every small deduction. Now, what's that doing? Is that doing something to column 1? I don't know. I don't know. I mean, so I know these 3 squares have have to add up to whatever those two squares are. So maybe we just try and minimize these and maximize them and see what that does to the columns. Is that a sensible thing to do? 10, 32. Oh, good. Oh, right, sorry. Okay, yes, this is a good idea because that breaks in half immediately. If you go 6, 7 here, so if we minimize those two squares, that's 13. Well, now these 6 squares have to add up to 32, but the minimum value of those two squares is 15. If we went 9 in one and 6 in the other, 32 and 15 is 47, and I've not even counted that square. So we're going to have to maximize these. So if we maximize these, let's look at that. If this is 8, 9, 17, so then we'd have 28 here. Oh, this is it. Right, okay, got it. Got it. Now this is huge. This is huge because now these add to 28. The minimum value for those is 15. That takes us to 43 with this digit left to place, and it can't be a 1. So it has to be a 2. And these two squares have to add up to 15. And we know one of them is a 9. So this is a 6, 9 pair. We know these are an 8, 9 pair. It's the only way we can keep these low enough to make the total work. Oh no, we haven't got a triple there. Okay. Now, this is very interesting indeed because we've got a 6, 9 pair here, but we know that whichever one of these is a 3 is a 9, 8 pair. Well, you can't put an 8 in either of those squares, so there must be an 8 in one of those squares, and we know that the other square is a 9 because there must be a 9 in one of those squares. So this is an 8, 9 pair. So now one of these rows is 9, 8. And the other one is 9, 6. So 9, 6 is 15. So, okay, what's that telling me? Is that telling me it's going to be very hard to make this add up to enough? Probably is, isn't it? So if whichever row adds up to has a 9 and a 6 in it, we know that 9 and 6 is 15. So the 7 cells in the middle have to add up to 30. But I've got to do that in a way that is legitimate with these 14 cages. 30. Yes, I see. This is incredibly well set. It really is. Every deduction it feeds back. All of these deductions feed back into each other, and we're getting loads of max-min constraints. But let's think about this. We know that the wings of either of these 14 strings, these wings here, the ones that stick out of the row we're interested in, have a minimum value of a 1-2 pair. So let's imagine that we go for a 1-2 pair in those two squares. That maxes out these. It maxes them out at 25 because that's 14 plus 14 minus 3. 25. So the absolute maximum we can make these squares is 25. 25 plus 15 is 40, and we know that the absolute maximum we can make either of these squares is a 5. So one of these is a 5. Is what we've just worked out. And one of them is a 3, so there's no 4 there anymore. We don't know which one it is, though. So we better get rid of the 1-2 pair. So one of these is 5, 6, 9. The other is, oh, I see. Right, okay. So either way, these 3 squares in whichever row we're looking at add to 20 because they're either 3, 8 and 9 or 5, 6 and 9. So in fact, the wings are always 1s and 2s. It's just beautiful. 1s and 2s which we could colour, I note immediately. Oh, I'm going to do that. Am I going to do that? Yes, of course I am. Yes, I am. Okay, so let's colour these in. Let's see what we get. Oh no, I better not use purple. Let's get rid of purple altogether. Or I can do them purple now. I don't think I need to colour those in anymore because I know what they are. So this is purple. That can be green. This can be green, therefore that's purple. Now, can we use that to our advantage? A little bit. This square. Oh no, hang on, I've got to be really careful here. I've got to be really careful. Because although it's true to say this square can neither be a 1 nor a 2, this 1-2 pencil marking is probably going to lead me astray here. Do I know that there's a 1 or a 2? Do I know there's a 1-2 pair in this 14 cage? Oh, actually I do. Yeah, okay, I do know that. Because I know that I need a 1 and a 2 in these 6 cells. So whatever this colour is, can't appear in those 3 squares because it would repeat in its cage. So it must appear in these 3 squares. And therefore, it has to be there. One of those 2 squares has to be purple. And presumably I can do the same logic the other way round. These squares can't be green, but there must be a green in these 6 squares, so it must be over here and it's not there. Oh yeah, okay. And that's not green, because green's in the box with it. So that's green. And we have another colour. Okay. Oh, if I knew whether green was 2 or not, that would be brilliant in those 2 squares. Okay. That square can't be a 1 or... Oh yeah, okay, so I've got analogous logic at the top. Yes, and that might get me this square, presumably. Yes, yes, no. No, yeah, yes it does. I need to put purple in these 6 squares. Those can't be purple. That can't be purple. That can't be purple. This is purple. So let's get rid of the 1s and 2s. Put a 1 or a 2 here. Make it purple. And have another stare. Ah, now I've got a 1-2 pair look in box 9. 1 and 2. And the 1s, 2s pairs here mean those 2 squares are a 1-2 pair. Don't know if I can colour them though, because these 1s and 2s are not telling me much about their colour. Okay. Nearly. Purple, purple. One of those 2 squares is purple. But I don't know if we know that... If we knew this wasn't a 2, we would know this was purple. Sorry, I'm sure that there's... I'm sure that there is a way we could be doing this. Ah, that can't be... Right, maybe look at... Oh no, we know one of these 2 is green already, Simon. Come on, use your brain. Ah, green, green. One of these 3 is green. That's not green by Sudoku. You can't ever put green in a 27 cage because it's a 1 or a 2. And that's going to break this cage. It's too low a number, so that must be green. Still doesn't tell us whether green is 1 or 2. Let's label it up though. And okay. Oh, beautiful, beautiful. Look, this 12 cage. You can't put 1 or 2 here. It sees both colours of 1 and 2. You can't put 1s and 2s there. It sees both colours. So, if you can't put a 1 or a 2 in a 12 cage, 3 cells, it's 3, 4, 5. That means that... I don't know what that means. I feel like this is right on the cusp of giving me something useful now. Oh, you know what? Look, look. I know those squares. They add up to 9 now. Surely that means I know what those sum to. By the power of Sudoku. So we've got 53 plus 9, that's 62. We know the column sums to 45, so we know these two squares sum up to 17. So they are an 8-9 pair. And that is not a 7. Ooh, and that's an 8 or a 9. So that means we need, in this column, we've not placed 4 and 6 actually. We can put 4 and 6 pencil marks at the top. 6, 10. Ah, I see. Yeah, okay. If we look at this shape now, it's got a 4 and a 6 in it. That adds up to 10. So the other squares must add to 17. So that means we know that the composition of this cage now is 4, 6, 8, and 9. This one sees 8 and 9. That's not 8 and 9. Oh, look. The 8s and the 9s are seeing each other. So we've got to colour those as well, presume. Oh, this is gorgeous. Right, okay, I'm doing that. Red. Make that one blue. That can be blue. That one must be red. Do we know this one? Oh, and that one? Oh, yes, yes, a 19 cage in 3 cells. Is it possible there's no 8 or 9 in this 19 cage? The answer is no, because 5, 6 and 7 add to 18. So there is at least an 8 or at least one 8 or 9 in the 19 cage. And look, these two cells see both 8 and 9 by colouring. So this square has to be an 8 or a 9, and it's blue because it's not red. Good grief. Oh, look, we now know blue. I've got blue. Blue. Blue, blue. Where does blue go in box 1? It can't repeat in the same cage as itself. So blue is in this corner. Blue is 8 or 9. Well, this corner cannot be an 8, so it is a 9. It's blue and it's 9. And therefore blue is 9 everywhere. And therefore, yes, and therefore that's 8, that's 9. We can do loads of colouring. All of the reds turn 8. Another slightly strange sentence. I appreciate that. 8's a red. Oh, look. Where does look. Where does 8 go in box 2? It can't repeat in this cage. That's why I've just removed the pencil marks there. There's an 8 here. 8 can only go there. Put it in. Change its colour. 8 is not here anymore. 8. Ah, come on. 8s, 9s. Yes. Where does 8 go in box 4? It's not there. It's not here, because that can't be an 8. It can't repeat in the 22 cage. Can't be here by Sudoku. Oh no, it could be in the 14 cage. Bobbins. Sorry. It can be in the 14 cage. I was about to write it in. That would have been an error. But it does give us an 8 here by Sudoku, so we'll take that and colour it in. Nine, look, now, by Sudoku is not in these squares. Where does 9 go in box 5? It has to be here. This square is blue, and it is 9. Which actually isn't very useful. Where does 9 go in box 3? It's got to go here. Which places 9 here. Okay. And now we can... I don't know what we can do, but it's quite exciting now. We can... 17. Yes, this is a 1-5 pair. Those two add up to 17. These two have to add up to 6. They don't include a 2. So that's 1 and 5 in some order. Don't think we know what that order is though. Okay. There's an 8 in this 26 cage, just looking at the options. That 8 is not there, so this square's an 8. And therefore it's red. 8 goes here by Sudoku, lovely. 8 therefore goes, yes, there by Sudoku, I think. Good, oh, this is going to be huge if that's true. I think it is true. And that means 8 is here in the 14 cage. Wow. Which means, well, it means this is not 8. It means we know that this square is purple now. And it means we know this square is 3 because 8, the only way of making a 14 cage work is with 1, 2, 3 and 8. So this is the 3. That's 5 therefore. That's oh, we could have done that, you know. Once I knew that was 9 and 8, we knew that that must accompany the 3. I just forgot that. This square's a 6. So now this row needs 4 and 7 into those squares, which is not resolved, but is very beautiful because it shows that we're probably solving correctly at the moment because it makes the 14 cage work. So how do we finish this off? We've got to we know these 3 squares now. They're 3, 4 and 7. Oh, sorry, my daughter's crying. I have to just go for a second. 1 second. About that. That's taken a lot longer than I was expecting. Initial arguments about Frozen and Postman Pat one thing led to another. Anyway, I am back now. It's actually 3 hours later, so I have not got a clue what I was doing. Those are highlighted. Let me just see what I last did. Okay, so I put 3, 4 and 7 into column 1, and it actually looks like we're getting on okay here, so perhaps we're... In fact, it's odd what you can see when you come... Look, purple has to be 1 or 2, and this square has to be 2 or 7. So purple is 2. I wonder how long ago that's... Hang on, I'm just going to go back and see how long ago... How long have I known that for? Quite a while by the looks of it. I'm not going to go all the way back. That seems like it could be a very long time. Anyway, purple is 2. Green must therefore be 1. Now we don't know about those 2 yet, so let's do greens manually. That's therefore going to be green. The purple in the corner must be a 2. Still don't quite know what's going on with the... We've got a 1-2 pair there. We can probably get those, but I can't see how. 1 has to be in one of those 2 squares by our old friend Sudoku. In box 7... yeah, look, in box 7, 1 has to be in one of those 2 squares. Well, it can't go in the 19 cage because that will require a second 9 and that will break for all sorts of reasons. So we can get the 1 here, and that's good because that gets us the 1 and the 2 over there, which gets us the 7, which I could have done the moment I got the 2, of course. It's funny what you don't spot. Now, 7 goes here. So should we tidy up the 2s? Let's make sure we get purples. Colour those in green. Purple is forced into this square in box 8. This domino adds up to 10. It's not 2, 8 or 1, 9, so it's 3, 7 or 4, 6. Let's actually see whether we can resolve that either, I'm afraid. 7, 4, 6. This 1 means there's no 1 there, which means this square's a 1. That square's a 5. 5 is now in one of those 2 cells. Keep going. Colour the 1 in. Get the 1 at the top as well. Look, now we know that one of those squares is 1. We know it must be this one. This one can lose its colouring and its pencil marks. And we've done all the 1s. Have we done all the 2s? No. We can do all the 2s though. Let's finish off the 2s. These 2 squares sum to 11. I think I remember that from earlier. Didn't all the 14s have to have 11 in them as well as their 1s and 2s? Now what do we do? We can 3, 4, 6, 7. So 5 in box 7 is in one of 2 positions. Same must be true of box 8. Wow, it's still definitely not giving up, is it? 7 in this box has to be at the top. So 7 in box 3 has to be on the right. 7, no. 7 in box 9 has to be in the top. That's nice. That gets at least a couple of pencil marks. Yeah, look, now I've got a 3, 4 pair here. In fact, I've got a 5, 7 pair here as well. This is really very important, I suspect. We've got 5, 7 here, 3, 4 here. This square now has to be a 7. That's not a 7. There's now no 7 in the 19 cage, in which case there's no 3. We've now got a 4, 6 pair. You can see the 3, 4 pair resolves it. 6 and 4 go in. Those 2 squares have got to be 3 and 5, I think, which fixes the 5 and 7 at the bottom. Lovely. 7 is in that domino. This column needs 4 and 6 into those top 2 positions. So these 2 squares are 3 and 7. Can we not do that? I suppose we can use that. That's got to be 5 or 7 now to make this domino add to 11. Wow, okay. Oh, the bottom row maybe? 3, 4s and 6s? No, maybe not. I'm not sure I get any... I get no 3 in this one. This is a 4 or a 6. No, that's useless. 3, 4 or 6. No, nothing's working. This needs 4, 6 and 7 into that square. Sorry, I must be missing something very simple here. 5s are in those squares, no 5 here. 5. Probably we need to resolve this 3, 4, 5 somehow. 3, yes, maybe I can do it that way. So there's a 3 in one of those two cells, no 3 here. Or maybe I can't. 7. 6 has to be in this domino. No 6. No, that doesn't do it either. 6 has got to be in one of those two squares. Good grief. Wow, this is actually not easy. Oh, right. Where does 6 go in column 7? It's not here because I've got 6s in those two squares. It's not here because there's a 6 in the row. So I think 6 can only go here, which does nothing except maybe clarify row 8 a little bit more, where we need 3s, 4s and 5s. 3, 4, 5, 3, 4, 5. This column, we need 3s, 4s, 5s and 7s. There's no... this 6, right, okay, maybe that. Has that done it? No? 3, 4, there's a 6 in one of these. I am floundering. 6 in one of these squares. 3. So... what on earth am I missing here? I don't know whether I should be looking for something really complicated or something. I suspect I'm missing something incredibly easy, and that's that's so bad. 3s, no. Oh, I'm sorry about this. 7s there. 7s. 5s. I can get rid of 5 from that square. Is that any use? Yes it is. It gets me a 4 here. Good grief. Right, this is not easy. Look along row 2. Row 2, we know that there's a 5 in the 12 cage, and the 5 is in one of those two cells. Let me highlight them. There's definitely a 5 in these two grey cells. In row 8, and this is actually how I spotted this, I'm always quite interested when a digit can only go into exactly 2 positions in a row. Those two squares are the only squares that can contain a 5. So compare these. Now, is it possible that this square here is a 5? And the answer is no, because if this square is a 5, you have to repeat the 5 in column 6 there. And this is a basic skyscraper pattern. It's where a digit is locked into exactly 2 positions in 2 different rows or columns, and one of the rows or columns aligns. So the way to think about it, this one actually is the wrong way round to be a classic skyscraper, but we know that if there's a 5 here, there must be a 5 there. And the only other thing that could exist, if this is not a 5, this is a 5. So we know one of those two squares is definitely a 5. And therefore you just hunt in the grid for any cells that see these two squares and know they can't be 5. That's the obvious one. So this can't have a 5 in it. Once this can't have a 5 in it, look at row 1. 5 has to appear in one of those two squares. Why does that matter? Well, I can see, therefore, this square can't also be a 5. So I think that's a 4. That might, yeah, this might be good, because now I've got a 6-9 pair here, look. which makes this square a 4. And that gets me a 7 there and a 4 here. It also gets me a 3 here and a 5 here. That gets me a 3 and a 7. Now, does it keep going or does it peter out? We need it to keep going a bit longer, I think. This square's now a 6 by our old friend Sudoku. That gets us a 4 at the bottom. Yeah, that's nice. 3 here, 6 here, 4, 6 pairs. So these two square... we need 3 in the box. That's a 3. That's a 5. That's a 3. Yeah, it looks like it's starting to tumble now, doesn't it? 5 has to go in one of these two cells. Those two squares include a 4, and there's a 4 here. That's good. We get the 4 and the 7. 4s have got to be in one. Yeah, 4 here, 7 here. This square here has got to be a 6. That gets us the 6 and the 4. This 4 allows us to complete that 11 pair, which completes the 14 cage. That's got to be a 5 by the same token. That's a 9. That's a 6. 6 has got to go there. If I trust my pencil marks, 5 and the 3 go in. 3 goes here. That looks good. And 7 goes here. And that all looks like it's done. Fantastic. What a great puzzle. That was very hard and very interesting. The way that these L-shaped tetrominos interact, it's clever as well, because it points you in the right direction without being enough that it becomes in any way straightforward. So I think in fact, look, there is a 5 in the middle. That was my first instinct, was that there was tension around row 5 and column 5, pushing this square, you know, pulling it and pushing it in either direction. So it sort of equalizes out at a 5. But actually proving that was a 5 was really difficult. And it's lovely logic, the way that we managed to limit the options for the gap cells in column 5, and the way these 14 cages worked in the rows. What a debut, Emmett. Fantastic stuff. Thank you so much for watching. It's another long video, but I make no excuses for that, or apologies. And we'll be back later with another edition of Cracking the Cryptic.